Hello everyone, welcome back to this online class. My name is Francis Okech and my YouTube channel is Professor Francis Okech. So today we are going to look at Calculus 2 and our main topic is integration via partial fraction decomposition. So before we look at how to integrate, we first of all need to understand the concept behind partial fractions. So under this, we are going to write. Now, we talk of the partial fractions. We can say the method of partial fractions The method of partial fraction decomposition is used when integrating a rational function of the form. So your integrand f of x, it should be of this form, p of x over q of x. So you're integrating f of x with respect to x. So it is a rational function where we have a numerator and also denominator. Now, p of x and q of x, those are polynomials. So we can say where p of x and q of x, these are polynomials. You know what we mean by a polynomial? And also, you write, and q of x, the denominator consists of products. Q of x consists of a product of linear and or irreducible quadratic factors. So you may have a product of linear factors or quadratic factors or a combination of the two. Now, what do you mean by a linear factor? Take note that what we are calling a linear factor is something like this: ax plus b. This is what you are referring to as a linear factor. And what you are calling a quadratic factor is ax squared plus bx plus c. This one is a quadratic factor. And it is only a quadratic factor if it cannot be simplified. It's a quadratic factor only if it cannot be factorized further. So if you have a quadratic expression that you can factorize, then that is not considered as a quadratic factor. What we call a quadratic factor is a quadratic expression that you cannot factorize further. I'll give you an example. I didn't give you an example of a linear factor, so let me give you an example here. For the case of linear factor, let me use another color. And I can use green. So for the case of a linear factor, you may have something like this: 2x plus 3. That's a linear factor. For the case of a quadratic factor, e.g., you may talk of x squared plus 1. You see, this one you cannot factorize further. That's a quadratic factor. Any other quadratic expression that you cannot factorize further is called a quadratic factor. Maybe I can give you another example of a quadratic factor. We can write, already we have x squared plus 1. Another one can be this kind of a factor. Another one, you can have 3x squared plus 7x plus 13. You cannot factorize this because you will need two numbers whose sum is 7 and product is 26. Do we have those numbers? No. So that's a quadratic factor, etc., because we cannot factorize them further. Take note that. You can just write note that when we have this factor, note that the factor, when I write x squared minus 4, this is not a quadratic factor. This one is not a quadratic factor. I can write with another color. Is not a quadratic factor. Why is it not a quadratic factor? It is because x squared minus 4 is simply difference of two squares, which you can write as x minus 4 times x plus 4. So you see this is a product of two linear factors. So this one is a product, let me write that in a better way, product of two linear factors. So it is not a quadratic factor because it can be simplified to get a product of two linear factors. What we refer to as a quadratic factor is a quadratic expression that you cannot simplify further or cannot be factorized. So having explained what we mean by linear factors and quadratic factors, those are the kind of products that we need in the denominator for you to be able to use the method of partial fraction decomposition. Now, once you have an integrand of that form, what next do you do? How do you decompose the integrand? So the next thing, even before you start decomposing or using this method of partial fractions, there's something that you must take note of. Another note is that we must ensure that the polynomial in the numerator must be of degree less than that in the denominator. So we can write this, that the requirement is that the degree of p of x, that is the polynomial in the numerator, must be less than the degree of q of x. So whenever you deal with partial fractions, always carry out a check to ensure that the numerator is of degree less than that of the denominator. If that is not the case, then what do you do? So I can use another color. Let me use blue to explain that concept again. If this is not the case, if this is not the case, comma, then use long division to simplify the integrand. Use long division to simplify the integrand f of x. When I say this is not the case, it means that the degree of the polynomial in the numerator is equal to or greater than that in the denominator. Before even you decompose your function, first of all, use long division so that you can be able to simplify that function. So I hope that is taken home. That's very important. You must take note of that. Now, if everything is okay, then how are you supposed to now decompose your function? So when you talk of decomposing, we are simply expressing that function as a sum of simpler rational functions that you can easily integrate. That is what we mean by decomposing a function. So you can just write here that what you mean by decomposing. To decompose f of x what does it mean? It simply means that you express f of x as a sum of simpler rational functions that can be easily integrated. Simpler rational functions that can be integrated easily. So that's what you mean by decomposing a function. You see, it's like you have 1/2. How else can you write 1/2? 1/2 is the same as the sum of what and what. That's what you mean by decomposing. So we can just say e.g., if you have 1/2, just this kind of a fraction, you see 1/2 is the same as 3/4 plus, I can talk of 3/4, not plus, but minus. I can now use minus 1/4. So it means we have decomposed the fraction 1/2 into these other fractions, because 1/2 is the same as 3/4 minus 1/4. Now, you see, when you talk of integration, our integrand will be a function of x. This is a case of a constant. Just to explain what you mean by decomposing a rational function or fraction. So there are 4 cases that we are going to consider. So we consider 4 cases. And the first case is, I'm going to write it. I can write case 1. Case 1. That is when q of x, remember q of x is the denominator. So when q of x consists of non-repeated, non-repeated linear factors. So when we have something like that, this is what I mean. It's like you have your f of x is equals to, e.g., f of x is equals to p of x over our denominator. We could talk of a1 of x times, plus b1, a1 x times x plus b1 times a2 x plus b2. There are so many, because this is a general case, times so many other linear factors up to an of x plus bn. So when you have this one, what are you supposed to do? So we are going, because you see, when the denominator is linear, the numerator must always be a constant. And when the denominator is a quadratic factor, the numerator must always be linear. So to be able to decompose this is how you're going to write it. It will be equal to, you assign some constants, call it a1 over a1x plus b1, then plus another constant a2 over a2 times x plus b2. So you follow the same pattern all the way up to the last one, a subscript n over anx plus bn. So what you need to take note of is, when you have a linear factor in the denominator, whatever you should have in the numerator must be a constant. Like you can see in the case of a1x plus b1, we have a1 capital in the numerator, which is a constant. So usually the task here is to find the values of the constants in the numerator. That is a1, a2, all the way up to a subscript n, the capital A's. Those are the ones that you need to determine their values. And once you know them, then it means we have decomposed our fraction f of x into those n rational functions, which you can easily integrate. So I'm going to give you an example. An example is this one. Example. So in this example, we are told to evaluate the integral of, let me look for a simpler one. We need to evaluate the integral of 2x plus 1, 2x plus 1, everything over x squared minus 1 dx. So you want to evaluate that integral. So how do you go about this integral? That is the question that you need to ask yourself. So if you look at this integral, you realize that the denominator is a difference of two squares, which we can factorize to get a product of x minus 1 and x plus 1. So that our integral can be written as, this is the same as the integral of 2x plus 1 over x minus 1 times x plus 1. Integrate with respect to x. So look at those linear factors. X minus 1 is a linear factor. Another one is x plus 1. They are non-repeated. None of them is repeated. So we need to decompose this into its partial fractions. So we are going to say that let me use another color. Let 2x plus 1 over x minus 1 times x plus 1 be equal to, so because of this linear factor, the first one, x minus 1, Our numerator will be a, let's say a over x minus 1, then plus. We also need another one corresponding to x plus 1. The numerator must be another constant. You can call it b over x plus 1. So our task is to evaluate or to simply find the values of the constants a and b. So if I multiply this by the LCM, I'm multiplying by the LCM on both sides. Look at our LCM is the product of x minus 1 and x plus 1. We are going to get a times x plus 1, then plus b times x minus 1 is equals to 2x plus 1. I have multiplied this equation, both sides, by the LCM to get this equation. Look at the one I have multiplied. This one is what I have multiplied by the LCM to give us the new equation, which I'm now calling equation star. Now, there are two ways of finding a and b. The first method, we write method 1. Method 1 is that of elimination. What does it mean? I'm going to choose some values of x that will help me eliminate some terms on the left-hand side. So for instance, if I want to eliminate the second term on the left-hand side, I have to put x is equals to 1. So you put or substitute x is equals to 1. Why are we doing this one? Because I want to eliminate the second term on the left-hand side. So what will we get? It will be a in bracket 1 plus 1 because x is 1, then plus b 1 minus 1 is equals to 2 times 1 plus 1. So that means 2a plus 0b, which is just 0, is equals to 3. So therefore, a is equals to 3 over 2. That's what we have. We also need to find b. To find b, just choose any other value of x. Remember, the starting value here must be a value of x that will help you eliminate some terms. Once you have found that starting value, the other values that you choose are any other values as long as you have found the starting value. So I could use 0 where there is x, or you could use -1, whichever. You are still going to get the same answer. So let me use 0. Put x is equals to 0. It's always good that you choose smaller values which are very close to 0, because it's easy to work with the smaller values. So with where x is 0, we'll be having now a into 0 plus 1 plus b times 0 minus 1 is equals to 2 times 0 plus 1. So when you work it out, you realize that we have a minus b is equals to 1. But you know a is equals to 3 over 2. So I'll write this one 3 over 2 minus b is equals to 1. And so you can make b the subject from here. What will it give us? 1, or simply 3 over 2 minus 1, which is 1 over 2. So b will give you 1 over 2. Now that we know a and b, we now go back to our integrand and replace these values. So we can now say that therefore 2x plus 1 over 2x plus 1 over x minus 1 times x plus 1 can now be written as a, which is 3 over 2 over x minus 1 plus our b, which is 1 over 2 into x plus 1. So, and this, you see 1 over 2 is common. So this you can also write as 1 over 2. And then we have 3 over x minus 1 plus 1 over x plus 1. So that's what we have. And so that is what we need to integrate. So instead of the given integrand, we are now going to replace it with what we have found. So this is method 1. Another method of finding the constants a and b, let's call it method 2. Method 2 is now we are going to expand. Look at our equation star, the one we are calling star. We are going to expand the left-hand side so that we have a times x. Let me use another color. Ax plus a plus bx, this is a plus, then minus b should be equal to 2x plus 1. And then you collect like terms, or we start with the coefficients of x, that is a plus b times x. Then the constant terms are a minus b. That should be able to give us 2x plus 1. Then now equate the coefficients, the corresponding coefficients. When we equate the coefficients of x, coefficients of x, you realize that we'll have a plus b is equals to 2 on the right-hand side. So this will be your first equation. Then we also equate the constant terms, On the left, we have a minus b. And on the right, we have 1. So this will be equation 2. So you now need to solve these two equations simultaneously. If I add them, I'm going to get 2a. Let me write there implies. If I add the 2, what will I get? I'm going to get 2a, because the b's will disappear, is equals to 3. So you make a the subject. So from here, you get a is equals to 3 over 2. And once you know a, it is easy to get b. You substitute the value of a, which is 3 over 2, into either equation Roman 1 or equation Roman 2. So when I substitute into equation Roman 1, what will be our b? Because where there is a, you are going to put 3 over 2. So our b will be 2 minus 3 over 2, which is simply 1 over 2. So that's another method. So when you are finding those constants, choose whichever method that is easier for you. Remember, I have explained these two methods so that you decide on which method is easier for you. But the restriction in the first method is that the starting value must always be that value of x that will help you eliminate some terms on the left-hand side. That is the only restriction. Remember, if you cannot find the starting value in method 1, then go for method 2. Because method 1, the starting value has to be that value that will help you eliminate some terms in equation star on the left-hand side. So, having found the values of a and b, now you see when you substitute, you're going to get this kind of fractions. And now that's what you need to integrate. So now back to our integral. So we can now say that therefore, the integral of 2x plus 1 over x minus 1 times x plus 1 dx. This is the same as the integral of 1 over 2. What did we get? 1 over 2, then 3 over x minus 1 plus 1 over x plus 1. So times 3 over x minus 1 plus 1 over x plus 1. Integrate with respect to x. And you see, this can be written as, this you can as well write as 1 over 2 times the integral of 3 over x minus 1 dx. Of course, this is bracket, plus the integral of 1 over x minus 1 dx. So now you know the techniques of integration. When you integrate 3 over x minus 1, you're going to get 3 ln x minus 1. So our answer is 1 over 2. And inside the bracket, we have 3 ln of x minus 1. Plus the other one you get, remember here it was a plus. So let me change it. This was a plus, the second fraction. So that will be ln of x plus 1. And remember, don't forget to write the constant c of integration. So that is your answer. You could simplify this answer using the laws of logarithms. This can as well be written as, can as well write this as 1 over 2. You see, when you apply the third law, this one becomes the power of x minus 1. So it will be ln of x minus 1 squared, and not squared but cubed, because that is 3. Then because of a positive, we are going to be multiplying. So let me write this in a better way now, because it's a multiplication, not division. So this I could write as ln of x minus 1 cubed times x plus 1 is x. So ln of that one, then you add to a constant c. So that is our integral. You see the way it is very simple. As long as you know how to decompose such kind of an integrand, then your work becomes very easy when integrating the resulting rational function. So that is case 1. Case 2. Let me write case 2. Case 2. So remember, we have 4 cases. So we still remain with 3 more cases. So in case 2, what kind of integral are we given in such a case? So in case 2, this is what we have. It's a case where you can write when q of x, that is the denominator, when q of x consists of linear factors. Consists of linear factors at least one of which is repeated. At least one of which is repeated. So you have a denominator where the factors are linear, yes, but you have some factors, at least one, can be one or even more, that are repeated. When I talk of repeated linear factor, let's say for the case where we have x minus 1 times x plus 1, you find that x plus 1 is squared or even cubed. That means it is repeated. If it is cubed, it means it is repeated 3 times. If it is squared, it is repeated 2 times, etc. So I'm going to generalize this case. So you can write e.g. Let me check this up so that I have enough space here. An example, a generalization is, you can write e.g. if your f of x is equals to p of x, so that is the numerator, over q of x is now this kind of a product. The first one is a1 x plus b1 times a2 x plus b2 times so many of them, there are so many, up to an of x plus bn, and we still have another one that is repeated k times. We can talk of cx plus d. This is raised to k. You see the last factor, cx plus d, is repeated k times. So in such a case, how are you supposed to write your fractions? So because this is linear, we'll talk of a1 over a1x plus b1. This other one is linear, talk of a2 divided by a2x plus b2. There are so many of them, up to the second last factor is also linear. This one, we'll talk of an over anx plus bn. And then the last factor, which is repeated k times, will give us another k fractions. So we'll have plus, now let's use b, talk of b1 over cx plus d. Then b2 over cx plus d, and this is now supposed to be squared, plus so many of them, b3, b4, up to the last one is, we are going to call it bk over cx plus d, and this is raised to k. So you see how the power is increasing the denominator. If the k is 3, you will go up to power 3. If k is 4, you go up to power 4. If k is 2, just reach up to power 2. So that's how you need to express your partial fractions when you have repeated linear factors. So we are going to look at one example of an integral to be able to illustrate this concept. So for example, of course, you realize that a1, a2, an, b1, b2, all the way up to bk, those are constants that we need to determine. So let's look at an example. And in this example, let's say we are asked to evaluate this integral. In the numerator, we have 3x plus 1. And in the denominator, we have x minus 1, and it is squared. X minus 1, the whole of this is squared, multiplied by x minus 2. Integrate this with respect to x. Now look at our denominator. X minus 1 is a linear factor which is repeated twice. So how do we decompose this integrand? So you write solution. We are going to say let 3x plus 1 over x minus 1 squared times x minus 2. This one, let it be equal to. Now, look at this linear factor. Of course, the numerator must be a constant, so it will be something like this. A, we can use A over x minus 1 plus another constant, just use B over x minus 1 squared plus, no, the first two fractions correspond to the first linear factor which was repeated twice. Then our third fraction will be corresponding to x minus 2. So the numerator you can write C capital over x minus 2. So that is what we have. Now our task is to be able to find the values of the constants A, B, and C. So we multiply this by the LCM. Our LCM is x minus 1 squared times x minus 2. So what are we going to get when you multiply by the LCM? So this will give us, we can say therefore, let me start by writing what we have on the right-hand side. In fact, we'll have A. Remember, I'm multiplying the whole of this equation by the LCM, which is x minus 1, and this is squared, then times x minus 2. So when you multiply, what are we going to get? We'll have A multiplying x minus 1, because it will cancel with one of them. Then here we have x minus 2. Then plus our B, this one will now multiply x minus 2. Then our C will multiply x minus 1, and that is squared. On the right-hand side, we should now be having 3x plus 1. So look at in case 1, I taught you two methods and that you need to use. Just use any of those methods that is easier for you, that will save a lot of your time. Now, I'm going to stick to the method 1 because I find it very simple for me. If it fails to work, then go for method 2. But if it works, then use it. Because you see, the restriction in the first method is that the value of x that you're choosing must be such that it can be able to eliminate some terms on the left-hand side. If that is not the case, then use method 2, which has no restriction. It has no restriction in method 2. So in method 1, let's see. If I want to eliminate any of those terms, I could use x is equals to 1. So if I put x is equals to 1 in that equation, let's call this equation star. So if we put x is equals to 1 in this equation, you see the first term will disappear because we'll have 1 minus 1, which is 0. What about the second term? Or simply let me write everything. It will be a into 1 minus 1 times 1 minus 2 plus b into 1 minus 2. Remember, x is 1. Then plus c into 1 minus 1. And this is squared. That should give us 3 times 1 plus 1. That's what we have. So the first term will disappear because of the 0 here. This is 0. So the whole of this will be 0. Even the third term will disappear. It will be 0 because 1 minus 1 is 0. So what do we remain with? It is negative b is equals to, negative b is equals to That will give us 3 plus 1, that is 4. So when you make B the subject, you divide by -1. So therefore, it means our B is -4. That's what you get. Now, we still need to find the values of A and C. Choose any other value of X. If you can find another value that will eliminate some terms, then use it. Again, if I cannot use 1 again. You realize that if I put X is equals to 2, we'll still eliminate some terms in that equation. So that means we'll have A into 2 minus 1, then times 2 minus 2, plus B into 2 minus 2, plus C is a plus, C into 2 minus 1, and this is supposed to be squared. That is squared, should give us 3 times 2 plus 1. So let's work out. Again, the first term will disappear because 2 minus 2 is 0. Second term, again, that is 0. So we only have the third term. C times 2 minus 1 is 1. 1 squared is 1. So that means from here, we're going to get C is equals to 3 times 2, that is 6 plus 1. That will give us 7. And we still need the value of A. So I need another value of X that I can use. Choose any other value. Let's use 0. Or we could use any value close to 0. I already have used 1. I could use -1 or whichever. But let me use 0. Any value is okay. So put X is equals to 0. What are we going to get? I'm going to get A. So here will be 0 minus 1, which is -1, times -2, plus B times -2, plus C times -1, and this is supposed to be squared, is equals to 3 times 0 plus 1. So with that, what do we have? It will now give us, now we have 2A, then plus, not plus, that's minus 2B, and then -1 squared is 1, so here we'll have plus C is equals to 1. But I know the value of B and C, so let me replace the value of B and C. So that will be 2A minus 2 times our B, which we got to be -4, plus C, which is 7, is equals to 1. So you need to make A the subject. So here we have 6 plus 7, that is 13. Divide by, no, then you take to the right-hand side. So we'll have 2A is equals to 1 minus 13. 1 minus 13, that is -12. So 2A is equals to -12, of which if you divide by 2, you're going to get A is equals to -6. So you see we have found the values of A, B, and C. Now we go back and substitute those into our given integral. Did we do it correctly? -2 times -4, that is positive 8 plus 5 plus 7, that is 15. So there's a slight correction here. It's not -6, but you see here, this is 8 plus 7, 15. When you take to the right-hand side, it becomes 1 minus 15, which is -14. Then you divide by 2, so you're going to get -7. So that's a correction, -7. So now go back to our function and rewrite it in terms of its partial fractions. So we can now say that therefore, this function here, which is 3x plus 1 divided by x minus 1, and this is squared, times x minus 2. This is supposed to give us, look at our a was -7, so this is -7 over x minus 1. Our b, we got -4, so plus -4 over x minus 1 squared. C, we got 7, so plus 7 over x minus 2. Now our task is to be able to integrate it to get our solution. So when we integrate, what are we going to get? So let me take this up. Now integrate both sides. We integrate this with respect to x. I can rub this equal sign so that I write it up there. I want to introduce the x here. I don't have the space, so I can rub this and write it somewhere here so that I can introduce the dx. Also integrate the right-hand side, everything with respect to x. So that's what we have. Now, what are we going to get when we integrate -7 over x minus 1? So that will give you -7 ln x minus 1. Already we have looked at so many techniques of integration, and so that's why I'm not emphasizing on which substitution you're supposed to make, but use substitution that will give you ln of x minus 1. Even the other integral, use substitution. So that will give you, that will now be +4. When you integrate, you're going to get +4 over x minus 1. When you integrate, you get that. And the other one will give us +7 times ln of x minus 2. Then remember there's a constant c of integration. Somebody might be wondering, how did I integrate the second term? Use substitution. Let u be equal to x minus 1. All of them use substitution. You're going to get the kind of integrals the kind of solutions that you have found here. So that is case 2. Now, let's look at case 3. Let me write 3 with the Romans. Case 3. So in case 3, we are going to consider quadratic factor which are not repeated. So I will write. So in case 3, this is a case where you can write when q of x, that is the denominator, contains irreducible quadratic factors. Contains irreducible quadratic factors. Let me write that in a proper way. Quadratic factors none of which is repeated. None of which is repeated. So we have that case. So what are we supposed to do in such a case? This is what you need to do. I'm going to give you a general example, like we can say e.g., let's say our f of x is equals to p of x, that is the numerator, and our denominator, let's say we have this kind of products. The first one is a1x. Of course, they are quadratic factors, and none of which is repeated. So let's say we have something like this. A1 x squared plus b1x plus, let's say we have c1. Another one is, we could talk of a2 x squared plus b2x, and the small b, b2x plus c2. There are so many of them up to the last one. Let's talk of an x squared plus bnx plus cn. Let's say we have such kind of quadratic factors in the denominator. So what you do here, you are going to write the fraction corresponding to the first factor. Call it a1x plus b1. Then over a1x squared plus b1x plus c1. So what you do realize that when the denominator is quadratic, the numerator must be a linear factor. Then plus, we'll have here plus, let's say we have a2x plus b2. This one is over a2x squared plus b2x plus c2. There are so many of them in between up to the last one. That will be, we can call it an x plus bn. This is over an x squared plus bn x plus c subscript n. So when you have quadratic factors, that's how you are supposed to write your partial fractions. And these capitals a1, b1, a2, b2, all the way up to an, b subscript n capital, those ones are the constants that we need to determine. And so we also need to look at one example here to explain how to integrate when you have quadratic factors in the denominator. And I told you, you might have a combination of linear factor and quadratic factor. You know what you're supposed to do now when you have a linear factor, the numerator must be a constant. So when you have a quadratic factor, the numerator must be linear. So let's see this one now. you can write example. Example. In this example, we are asked to evaluate this integral. We have the integral of, let me give you a simpler one. In the numerator, we have x squared minus 1, x squared minus 1, and in the denominator, this one, in the denominator, we have x plus 2, x plus 2, then times x squared plus 1. We need to integrate this with respect to x. So what you do, as usual, you will say, of course, we need to know the numerator for x plus 2, which is linear factor, and this other one is quadratic factor. So we are going to say let x squared minus 1 over x plus 2 times x squared plus 1. Let this be equal to, now the first factor is linear, so we expect the numerator to be a constant. Let's call it a over x plus 2. The other factor, x squared plus 1, is quadratic factor, so that will give rise to this linear expression in the numerator, so that is bx plus c over x squared plus 1. When you multiply this equation by the LCM, what are we going to get? Remember, our LCM is x plus 2 times x squared plus 1. So multiply that equation both sides by the LCM. We're going to get a times b, a times, let me write this, a times x squared plus 1. This is added to bx plus c, multiplying x plus 2. And this is supposed to give us x squared minus 1. So this is the one we are calling equation star. Let me use another color. This is the one we are calling equation star. And I told you that there are two methods of finding the constants a, b, and c. Stick to one method, only use the other method. Stick to any method that is easier for you. And remember, method 1, the one we are calling elimination method, has a restriction on it that the starting value of x must be such that it can be able to eliminate some terms on the left-hand side. Very important. So when I substitute, let's see, you realize that if I put x is equals to -2, I will be able to get rid of the term containing bx plus c, because that will be bx plus c times 0. -2 plus 2, that will be 0. So that is the starting point, the starting value of x. So you write put x is equals to -2. That's what I use. So with -2, what are we going to get? We are going to get this, that a times x squared, that would now be -2 squared, which is 4, plus 1. Then we have plus, here now b times -2, that's -2b, plus c, which I don't know. Then this should be -2 plus 2 is equals to -2 squared, that is 4. We are subtracting 1. So what do we get? Of course, you see here, the whole of this term will vanish, that is 0, because of negative 2 plus 2, which is 0. So here we have 5a is equals to 3. 5a is equals to 3. That means our a will be equal to 3 over 5. So we have found a, we still remain with b and c. Let's find b and c. So once we know the starting value, which is negative 2, now to get the values of b and c, we can use any other value of x. Let me use 0. I can use 0. So we can say put x is equals to 0. What will you get? I'll get a, because where there is x, you put 0. B times 0, that is 0. So I'll have just here, I'll have c times 2. C times 2. And on the right-hand side, we'll have 0 squared, which is 0. And then we subtract 1. So that's simply negative 1. So here we have is equals to negative 1. But I know a is equals to 3 over 5. So let me replace. We have 3 over 5 plus 2c is equals to negative 1. Now, negative 1 minus 3 over 5. Remember, negative 1 is negative 5 over 5. Minus 3 over 5, that will be negative 8 over 5. And then you divide by 2 to get c. So this c will now be equal to negative 4 over 5. So we have found c. Now let's find b. I need another value of x apart from negative 2 and 0. Let me use negative 1. Whichever value is okay. So if I substitute x is equals to negative 1, what will I get? In the first term, I'll get a. Remember, negative 1 squared is 1. So we'll have 1 plus 1. Then I'll have here plus b. B times 1 is just b, then plus c. And this one, we are again, no, it was negative 1. So I have to rewrite this. So b times negative 1 is negative b, so not b. That's a correction. Here we have negative b plus c. Then here we have negative 1 plus 2. That will give us positive 1, so negative 1 plus 2. And on the right-hand side, negative 1 squared is 1, then minus 1. That's what we have. Let's simplify. We'll have 2a. I can use another color. I can pick blue. So here we'll have 2a. And then here, you see here it is 1. So that is minus b plus c. Minus b plus c should be able to give us 0 on the right-hand side. Substitute what we know. I know a is 3 over 5. So I'll write this as 2 times 3 over 5. I don't know b, so let it be minus b plus our c, which is negative 4 over 5, is equals to 0. So with that, what do you get as b? 6 over 5 minus 4 over 5, that is 2 over 5. And so that means our b will be equal to 2 over 5. b is equals to 2 over 5. So we have managed to find the values of a, b, and c. Now, let's go back to our integrand and substitute those values. So I'll rewrite it here. So you can now say that therefore, our integrand, which is x squared minus 1, everything over x plus 1, x plus 2, I mean, then times x squared plus 1 quadratic. This can now be written as, remember, our a is 3 over 5, so I can factor out 1 over 5 outside. So let me write this, I need a space. This should be equal to, factor out 1 over 5. Then inside, the numerator will now be 3 over x plus 2. The other one is bx plus c, and b is 2, so that will be plus. Remember, b is 2 over 5, and we have factored out 5, so that will be 2x. And our c, the numerator is negative 4, because I factored out the denominator. This is over x squared plus 1. So that's what we have as our new partial fractions. So you need to integrate it. You need to integrate the left-hand side with respect to x. Also, the right-hand side, integrate with respect to x. You see, 1 over 5 is a constant. That's why it is outside that integral. So the question is, what is the integral of 3 over x plus 2? And also, what is the integral of 2x minus 4 divided by x squared plus 1? When you integrate this, remember this can be written as 1 over 5 times the integral. Let me put in bracket. The integral of 3 over x plus 2 dx plus, here we'll have, I'm going to integrate this using the splitting the numerator method. We are going to split the numerator into these two integrals. It will be the integral of 2x over x squared plus 1 dx. Then the other one will be now minus the integral of course, 4 over x squared plus 1 dx. You see what I've used? I have split the numerator so that I make my work easier when integrating the second term, the second integral. So when you apply the techniques of integration, in the first part, you need to use U substitution. You let U to be x plus 2, and then you work it out. So this will give us 1 over 5. When you integrate this, we are going to get 3 times ln x plus 2. When you use U substitution, what about again the second integral? Again, another U substitution. Let U be x squared plus 1. So this will give us ln plus ln x squared plus 1. And the other one is negative 4 tan inverse. There you use trigonometric substitution. Let x be tan theta. So this will be tan inverse of x. And don't forget to write the constant c of integration. And remember, you could combine these natural logs so that you get one natural log. You could use the laws of logarithms, or you could just leave them as the way they are. And so this is our solution for that particular integral. Lastly, Let us look at case 4, where now we have repeated quadratic factors. So I'm going to write here case 4, case 4. So this is a case of repeated quadratic factors in the denominator. So we can just write here that when Q of X contains at least one repeated, contains at least one repeated irreducible quadratic factors. Irreducible here means you cannot factorize that quadratic expression. Irreducible quadratic factors. So, what are we supposed to do? Let me give you a general case of this kind of integrals. We can say, e.g., let's say we have something like this. We have f of x is equals to p of x, everything over. Let's say we have this linear factor. We can talk of ax plus b. Then the quadratic factor is repeated k times. Talk of already I've used a and b. I could use a1 and a2, or even a and b, whichever. And here I can use cx squared plus dx plus e. And this is repeated k times. So what are you supposed to do in this case? So this one will be equal to, take note, this is linear. So we expect the numerator to be a constant. We could use any constant. Talk of a1. Instead of, I could talk of a over ax plus b. And then the quadratic one, that is repeated k times, will give rise to other k fractions, rational functions of this form. So we can now talk of b1 plus, this is b1x plus c1 linear over, in the denominator we'll have cx squared plus dx plus e. Then plus another one is, now we can now talk of b2x plus c2. This is over cx squared plus dx plus e. And this is now squared. There are so many of them in between. So many of them. Up to the last one, which we can write as b subscript k x plus c subscript k, and this is over cx squared plus dx plus e, and this is raised to Okay. So that's how you're supposed to decompose such kind of a fraction, a rational function. Let us look at an example to illustrate this concept. Remember, A capital, B1, C1, B2, C2, all the way up to BK, CK. Those ones are constants that we need to determine. So I'm going to give you a simple example just to illustrate this concept of finding the constants A, B, B1, B2, all the way up to BK, C1, C2, all the way up to CK. So we write example. In this example, you are asked to evaluate this integral. Let me look for a simpler one. The numerator is x cubed plus 1. This one. Everything over our denominator is x plus 1 over x squared plus 1 squared. X squared plus 1, and this is supposed to be squared. So we integrate this with respect to x. Now look at our denominator. X plus 1 is a linear factor, and x squared plus 1 squared, that is a quadratic factor that has been repeated twice. X squared plus 1 is quadratic, and it is repeated twice because of the square there. So it means we are going to get 3 fractions. 1 for the linear factor and 2 for the quadratic factor, which has been repeated twice. So how do we work it out? So we are going to say that, let's write it. You say, let x cubed plus 1 everything over x plus 1 times x squared plus 1 squared. Let this be equal to, so corresponding to the x plus 1, that will be a, let's be a over x plus 1 plus, corresponding to x squared plus 1, the first fraction, let it be bx plus c over x squared plus 1. And the other one, because this was repeated twice, so we also need dx plus e. This is over x squared plus 1, and this is supposed to be squared. So those are the fractions, the rational functions that we need in this case. Now you need to multiply the whole of this equation by the LCM. Our LCM is x plus 1 times x squared plus 1 in bracket squared. So when you multiply that equation by the LCM, we are going to get this. You write, or, let me start by writing the right-hand side. It will be a times x squared plus 1 squared plus bx plus c. This one is multiplying x plus 1, x plus 1 times x squared plus 1. And the other one is, you write plus dx plus e. this one divided by, not divided, but multiplying x plus 1 to give us the right-hand side will be x cubed plus 1. So that's what we have. You see, now we have how many constants? There are 5, A, B, C, D, E. Those are 5 constants which you need to determine. And there are 2 methods. The first method is that of elimination, and the other method is that of equating the corresponding coefficients and solving for the resulting system of algebraic equations. I find the first method easy for me, and so I am going to use it. And the starting value must be that value of x that will help you eliminate some terms from the left-hand side. If you look at this equation star, you realize that, look at this term. I can use another color. Look at this term here. You realize if I put x is -1, it will be -1 plus 1, which is 0. That will help me eliminate the third term on the left-hand side. So that's what I'm going to start with. So another color, blue. So you can write put x is equals to -1. So with -1, what do we get? We are going to get, of course, A here. At A, we will have this one. We'll have A times -1 squared is 1 plus 1, that is 2. So this is 2 squared. Already I've worked it out. So 2 squared. Then plus -b plus c. Remember, x is -1. The other one is 0. -1 here. Here we are going to get 0. So that is 0 into -1 squared plus 1, that is 2. Then the other term, it will be -d plus e times 0, because x is -1, is equals to 0 plus 1, that is 1. Not 0 plus 1, -1 cubed. -1 cubed is -1. So this is -1 plus 1. So what do you realize? That this term will vanish, that is 0. Even this will vanish. We only have 4a is equals to 0. So from here, because this is 0, -1 plus 1, that is 0. So that will give us 4a is equals to 0, which means even a must be equal to 0. So a is not there, it is 0. Now, because a is 0, in fact, I don't even need this term. It means even this term is 0. We will not need it. We already know a to be 0. So that term will be 0. So that our reduced equation star will now start from bx plus c times x plus 1, then times x1 plus 1 plus dx plus e times x plus 1. And so that should give us x cubed plus 1. Now, what other value can you use? We can now use any other value. Let me pick 0. If I put x is equals to 0, what are we going to get? If x is equals to 0, we are going to get, of course, I don't need the first term containing a because a is 0. So that means even b times 0 is 0. So we start from c times 0 plus 1, that is 1. Then 0 squared plus 1, again, there's another 1, plus d times 0 is 0, so that will give us e. So that is e times 1 is equals to 0 cubed, which is 0, then plus 1, that will give us 1. So in short, what we have here is that c plus e, it should be equal to 1. C plus E is equals to 1. So you can call this equation number 1. Another one, remember we had 5 constants. So I need 5 values of x. So far we have 2 values. The third one, when you put x is equals to 1, what will you get? So we can also try with put x is equals to 1. X is equals to 1. What will it give us? Let's go back to our equation star, this one. With x is equals to 1, I'm going to get b plus c, and this is multiplying. That will now be 1 plus 1, which is 2, multiplying 2, and also multiplying 1 squared plus 1, another 2, plus d plus e. And this will again multiply 2 to give us 1 cubed is 1 plus 1 is equals to 2. So you see, I can see 2 is common, so that you simplify. If you work it out, if you divide by 2, you're going to get this. Divide by 2 on both sides to get 2b plus 2c plus d plus e. That should give us 1. So that's another equation. Call it equation Roman 2. I still need 2 values of x. Let me use negative 2. If I put x is negative 2 in equation star, put x is equals to negative 2, what are we going to get? Let's see. In the first term, we'll have negative 2b plus c plus c. Then here we'll have times negative 1, because negative 2 plus 1 is negative 1. Negative 2 squared, that is 4, plus 1, that is 5. Then here we'll have plus negative 2d plus e. And this is times negative 1 is equals to negative 2 cubed, that is negative 8, plus 1 is negative 7. And so when you work it out, let me open the bracket. If you open the bracket, you're going to get this equation. You can use another color, blue. When you open the bracket, you're going to get 10b minus 5c plus 2d plus e. No, this should be minus e. At E there's a minus because of that minus 1. So change this to minus. Instead of a plus E, it should be minus E. Minus E, that should give us negative 7. So this is the third equation. And lastly, when you use x is equals to 2, what do you get? Remember, we are substituting 5 different values of x because we have 5 constants. When you are solving a system of equations, there must be same unknowns as the same as the number of equations. So the last one, I want us to use 2 in place of x. Put x is equals to 2. What are we going to get when x is equals to 2? So in equation star, we are going to get this one. We are going to get 2b. So this is 2b plus c. Then here we'll now have 3. 2 plus 1, that is 3. 2 squared plus 1, that is 5. Then we have plus 2d. 2d plus e. This should multiply 3 to give us 2 cubed, that's 8 plus 1, that is 9. And then you also need to simplify this. If you simplify, we are going to get, because I can see 3 is common, so I could divide that by 3 so that I have 10b. Let me choose another color. This should now give us 10b, 10b plus 5c. Plus 2d plus e. Plus 2d plus e, and that is equals to 3. So that's the last equation. So your task here is to solve the 4 equations simultaneously. Solve the 4 equations simultaneously to get the values of B, C, D, and E. Already we have A is equals to 0. So when you solve using any method of solving a linear system of algebraic equation, the best way is to use elimination method or substitution method, which I know you can do. So you need to get this as your solution for those constants. B should be 0, so already A was 0. And when you solve equations 1 up to 4, you need to get B is equals to 0. C is equals to 1. C is equals to 1, this should be 1. D should be negative 1. D is equals to negative 1. And the last one is E should be equal to 0. E is equals to 0. So those are the values that you're supposed to get. So back to our integral. Look at our function now, the integrand which we have decomposed. It means here, this will be 0. So this is not there because A is 0. The E is also 0. So this is 0. And the B is also 0. So this one is 0. We only have values at C and D, where C is negative 1. So this integral cannot, this function cannot be written as -1, which, no, c is +1. +1 over x squared plus 1. So it is 1 over x squared plus 1 minus, d is -1, so that is minus x over x squared plus 1 squared. The whole of this is squared. So that is what you get when you decompose that kind of a fraction. So what is the integral of the first fraction? And what is the integral of the second fraction? So when you integrate this one, you're going to get tan inverse of x. So we are saying therefore, our integral, which was x cubed plus 1, is a plus 1 over x plus 1 over x plus 1. Let me write it. X plus 1 times x squared plus 1 squared dx. What is this supposed to give us? So we integrate this one. Of course, the integral of that will be tan inverse of x. Or I could write this as, let me write, it is now the integral of 1 over x squared plus 1 dx. Then minus the integral of x over x squared plus 1. And this is supposed to be squared dx. So that's what we have. Now, apply the techniques of integration to be able to work out those two integrals. So in the first part, we are going to get tan inverse of x. I can use another color. Let me use black. So here we are going to get tan inverse of x. What about the second integral? What do we get? We are going to use u substitution. So let u be equal to x squared plus 1. So that du is 2x dx. So I simply add here, you see, x squared plus 1. So I'm going to say u is x squared plus 1. X squared plus 1. So this means du dx, what will it be? It is 2x. Or you make dx the subject. So from here, you could talk of x dx, or simply du over 2. Du over 2 is the same as x dx. So what will this give us? That integral will now give us the integral of 1 over u squared times du. This is u over 2, which you can write as 1 over 2 outside the integral of u raised to -2 du. When you use power rule, add 1 to the power, then divide by the resulting power, you're going to get 1 over 2 1 over 2, then times u raised to negative 1, also divide by negative 1. So that's simply negative. You see, this can be written as negative 1 over 2u, 2 times u, because u raised to negative 1 is 1 over u. So that our answer here will be plus, not plus, but minus of negative 1, minus of negative 1 over 2u over 2 into x squared plus 1. So that is our integral. And remember to add c after integrating, after getting the final solution. And remember, a minus and a minus should be a plus. So this is a plus. And so that's our solution. So thank you all for watching this video. Please subscribe to my YouTube channel, that is Professor Francis Okech. If you go to the YouTube search, type Francis Okech or Prof. Francis Okech, and you will find me right there. Also, don't forget to share, comment, and like this video. When we meet next time, we look at other techniques of integration. Bye-bye.